Hello, students, and welcome. Have you ever wondered why some chemical reactions just don't happen unless you add something special to them? Well, today, we are going to explore one such very important reaction, the preparation of haloarenes. It might look a little bit difficult at first, but I promise you, by the end of this session, you will understand it perfectly. So let's begin with a small puzzle, something you might even observe in a chemistry lab. It involves a very stable molecule and a special little helper. Just imagine this. You take some benzene, you add bromine to it, and nothing happens. The reddish-brown color of the bromine just stays there. But then you add just a little bit of iron bromide powder, and almost instantly, the color vanishes. So what is going on? What magic is this catalyst performing? You see, figuring out this puzzle is the key to understanding how we prepare haloarenes. And this is not just about your exams, you know. This chemistry is fundamental for making so many important things, from medicines to even products we use in agriculture. Okay then, let's get right to the heart of it. It's time to reveal this special method that solves our little lab mystery. The answer lies in a special type of reaction called electrophilic aromatic substitution. Yes, I know, it's a very long name, but the idea is simple. The benzene ring is extremely stable. It's like a fortress. A normal halogen molecule can't do anything to it. It needs a very powerful attacker, an activated halogen, which can go and attack the ring. Now here is a very common mistake that students make. They learn how to prepare haloalkanes, often using free radical substitution, and they think the same method will work for benzene, but it absolutely does not. The benzene ring is a completely different case because of its stability. It needs a special method, and that method always requires a catalyst. So the big question is, how does this catalyst actually work? What is it doing? Well, to understand this, let's use a simple story, an analogy. Let's imagine the benzene ring is like a very exclusive club with very strong security. That's its aromatic stability. Now, the halogen molecule, like bromine, is just a normal visitor. It tries to get in, but the security is too strong. It can't enter. This is where our catalyst, the iron bromide, comes in. Think of it as the gatekeeper. The gatekeeper takes the visitor, the halogen, and gives it special credentials. It does this by pulling electrons away and turning the halogen into a powerful electrophile. Now, with these new credentials, the halogen is an authorized guest, and it can finally enter the club. So you see, this whole concept exists for one simple reason: the incredible stability of the benzene ring. We can't just use a brute force method. We have to be smart. We need to create an attacker that is strong enough to get in and replace a hydrogen, but without destroying the ring's special stability. Okay, now let's try to get a clear mental picture of this whole process. Think of it like a battle plan for attacking the benzene ring. So here is the plan of attack, step by step. First, the catalyst activates our halogen, turning it into a powerful warrior, the Br+ electrophile. Second, this warrior attacks the electron-rich fortress of benzene. Third, as the warrior attacks, the fortress walls are temporarily breached, and the ring loses its aromatic stability for a moment. Fourth, to make space for the new warrior, an old sentry, a hydrogen ion, is pushed out. And finally, the warrior is now part of the fortress wall, the defenses are sealed again, and the powerful aromatic stability is restored. So all this theory is fine, but where does this fortress attack actually happen in the real world? Well, you might be surprised to know that this reaction is used to make a product you might have at home right now. Why does all this matter? Because this exact reaction is used in industry. To make para-dichlorobenzene, which is the chemical found in mothballs and some air fresheners, they take benzene and they chlorinate it, not once, but twice, using this exact electrophilic substitution method with a catalyst. And let's just go back to that very critical mistake one more time so you never make it. You might think, okay, the free radical method works for alkanes, so it should work here too. We are just replacing a hydrogen. But no, it fails completely. The aromatic ring is far too stable for that kind of random attack. It needs a specific, targeted attack from a strong electrophile. All right, let's bring everything together. If you just remember these few key points, you will be completely prepared for this topic in your exam. So first, the core idea. Haloarenes are made by electrophilic aromatic substitution. This is different from haloalkenes. Second, the key player. You must have a Lewis acid catalyst, like iron bromide. It is absolutely essential to activate the halogen. Third, the mental image. Always remember the fortress and the warrior. The catalyst's job is to create the strong warrior who can attack the stable fortress. And finally, the real-world link. This is how we make products like moth repellents. So, when you see this topic in your exam, please don't get nervous. Just remember these simple things: the core idea of this special reaction, the mental picture of the fortress attack, and that one real-world application. If you remember that, this topic will feel much, much easier. All the best.